Okay, we're gonna continue on here and finish up chapter 14 after how long we've been on chapter 14? Forever. So the final little bit of here of chapter 14, we're gonna finish talking about. Obviously, last time we talked about one more type of titration, which was a titration of a strong acid with a weak base. And in this case, remember, in this type of titration, we're actually adding the acid to the weak base here. And as we saw in the sort of the titration curve, it is sort of upside down from the other one. And that's because we're obviously starting with a base. So we have a basic pH, and then we're going to drop into the acidic here. And as we talked about, this one is very similar to the weak base, strong acid, weak acid, strong base titration that we talked about in the middle. It really has the same four parts as to any one. Remember here at the very beginning, we pretty much only have a weak base, so it's a KB type of problem where you need to do an ice table, figure out the hydroxide concentration, and that will get you the POH, and then that will get you to the pH. Remember that as you start the titration to before the equivalence point, just like we saw with the weak acid, strong base titration, you will create a buffer in this range. So you will end up with a buffer type problem here. And that basically means, in terms of the calculation, you have to do at least one ice table. And the purpose of the ice table is basically to get the concentration of the buffer you just made in that region. And at that point, you can then go straight into the Henderson-Hasselbalch because it is a buffer. Or you could alternatively, again, do a second ice table instead of the Henderson-Hasselbalch. When we get to the equivalence point, remember in this situation here, we will again, like all equivalence points in a titration of acid and a base, you pretty much will just have a salt that's left over. And at this point, because the salt that's came from a weak base, we know that it will go through hydrolysis. And this particular salt will go through hydrolysis and produce H3O plus and will make the solution acidic at this point. So as we talked about last time, we talked about three different types of titrations: strong acid, strong base. We expect the equivalence point to be neutral, 7. Weak acid, strong base. Because of the hydrolysis of producing hydroxide, we expect the equivalence point to be basic. And in this type of titration that we talked about last time, also because of hydrolysis, because it's producing H3O plus, we expect the equivalence point to be acidic. So those three different sort of differences in equivalence points are based on the type of titration that you're doing. Once again here, that basically means that's going to be a double ice table type situation. First ice table is really just to get the concentration of the salt that you produced. And once you have the concentration of the salt, you're pretty much going to do a hydrolysis ice table where it reacts with water and produces, in this case, the H3O plus. And you'll be able to figure out the pH from that point. You will need to, obviously, like we talked about in most hydrolysis type situations, probably has to do a little swap of the K value there and convert it into a Ka value, which you would need from the Kb value that you're most likely given in this titration. Past the equivalence point, obviously, we are just dumping in acid at this point, and we do need to do an ice table. And really, at this point, what we're trying to figure out is how much of that strong acid we have left over. We will still have that same salt that we had at the equivalence point present, but in comparison, the strong acid is obviously a much stronger acid than the salt being an acid. And we ignore the contribution of the salt at this point, and we look strictly at the contribution of the strong acid. Any questions on any of those parts of the titrations there? All right. So let us finish this chapter officially. We've sort of touched upon this as we've been going through the chapter, but to officially sort of talk about acid-base indicators, as I mentioned before, you can think of an acid-base indicator as like a weak acid, and the IN here means indicator. And there's basically a protonated form where it has the hydrogen just like an acid, and it also is a deprotonated form where it sort of gives away its H plus, and it's basically the indicator with one less H plus. And depending on sort of the ratio of those versions of the indicator you have in your solution, you'll see basically one sort of color versus the other. Now, indicators have different colors a lot of times in acidic solutions and basic solutions, and they do change over typically, as we talked about. Indicators typically change over a specific pH range. So you typically will see a color change as the pH changes. And the idea obviously is you do want to pick an indicator that will change colors somewhere near your equivalence point, right? Because typically when we do a titration, unlike what we'll do in here where we do the entire titration curve, but like what you did in Chem 50, the point of a titration is to know kind of when to stop, right? And as the one you're probably again familiar with, which is phenolphthalein, you're looking for that very, very lightest color pink, and that indicates that you should be near the equivalence point, and you probably should stop your titration. Speaking of phenolphthalein, as we've talked about, again, it works from 8.3 pH to about 10ish, and once again, it's colorless here and again gradually gets pink and dark pink as you sort of move in this direction. And you can see here, here's a table of some different indicators and sort of the pH range as which they work. You can see you have a lot that, you know, kind of change color in the acidic range. You have some that sort of change color near the neutral range. And then you obviously have some here that change color in the basic range. And there is our phenolphthalein down here. And as you can see, a much pretty much colorless and then starting to get super light pink down to obviously some really dark fuchsia pink that maybe some of us have seen in titrations when we've done it. I like the dark pink color personally, you know, it's good. Um, so again, you can sort of really dial in your choice of indicator based on what type of titration you're doing. So as we just talked about at the equivalence point and the three types of titrations we talked about, one is going to give you a pH of 7, it should be, in terms of when it should reach the equivalence point. One should be an acidic one, and one should be a basic sort of equivalence point. So for example, if you were doing a titration where, you know, your equivalence point's acidic, you know, choosing phenolphthalein that works in the basic range is probably not a great choice for you, right? Because you're going to be way past, obviously, your equivalence point when that thing sort of turns. So you want to kind of think about the type of titration you're doing, where it should change, and sort of the color. And you know, it sort of locks into this color, and you can see most of them kind of gradually change to a different color. Some of them even change to multiple colors along the way. You get kind of like in this one, a yellow, green, and then kind of a bluish. And if you actually mix that one there with a little phenolphthalein, you get a nice like purple color at the end. When you do some titrations, it's kind of nice. So with that in mind, why don't you take a look here at the list? And again, we can see on this list the pH ranges where these types of indicators work really well. And based on okay, so let's take a look. And like I said before, you want to kind of think about the titration we got going on here. So HNO2 is a weak acid. And again, I know it's a weak acid because we just did the example. But more importantly, I know that it's a weak acid because it's not one of those 6 strong acids that I kind of know, that list of 6. And obviously KOH here is a strong base. So basically this titration, if you sketched it, will look something like this. Now, one of the things I do know is when I reach the equivalence point, I should have a salt that's left over. And because I have a salt that's left over, which in this case would be NO2 minus, by the way, it comes from a weak acid, which means the salt's going to act as a base when it goes through hydrolysis with water, and that means it's going to accept the H plus, and when it does, we'll make HNO2, and we will make hydroxide. So we should know that at this point in this type of titration, the equivalence point should be a basic equivalence point. And when we kind of go on this list here of indicators, clearly this one would not be a great choice since it's going to obviously change color way over here at my kind of titration, right? Which is not near my equivalence point. Um, If we go there, not going to be so good. Still acidic, still acidic, still acidic. Now, this one does get a little bit into the basic range, but not very much, to be honest with you, because at that point, if you think about just indicators in general, that's sort of at the end of the road there. And probably at that point, it's already changed color, probably before that, right? A little bit. So that's probably not the great choice. But that is not a bad choice because it is definitely at least into the basic range. And our good friend phenolphthalein is not bad as well because it's also in our basic range. So out of this list here, these two would be a really good choice probably. And like I said before, what you could do is calculations, for example, theoretical calculations of what your pH should be at the equivalence point, and you could actually, like I said, kind of dial in on the list of indicators available to you to kind of choose the most appropriate one. And again, obviously the idea, as we mentioned, is to get one that changes color as close to your equivalence point as possible so that when you're doing the titration, you know when to stop, basically, right? It's really what an indicator is a visual indication of the reaction's over, the titration's over, and you want to kind of stop. Any questions on that there? All right, dare I say, that is the end of chapter 14. Who would have thought it would ever end? All right. We're going to go off to chapter 15 now. Maybe. Oh, looks like a 15-ish. All right, we're going to talk chapter 15 here. Not a super long chapter. This is the second chapter on the next exam, exam 2. So we're going to talk about two other types of equilibrium constants because, we don't have enough K values at this point, right? We need to add some more. So we're going to talk about KSP and we're going to talk about KF in this chapter. And they are kind of for two different types of things. KSP is really the equilibrium constant for things that are insoluble. So when you think about solubility rules and things being insoluble, that is basically your KSP. KF, as we'll talk about, is the equilibrium constant for really complex ions. And they are kind of almost at two different ends of the extreme in terms of their numbers and how we sort of deal with these guys. So let's start with KSP. And when we talk about things, if you remember your solubility rules, which maybe they made you memorize them at 50, did they? Oh, maybe. That's not bad. There are certain things, obviously, based on solubility rules that when you put them together, you would expect them to make a solid. And one of the things when they do make a solid, and one of the things that maybe you may not be particularly familiar with is the idea that those solubility rules are not necessarily 100% always correct, in the sense that there are a lot of factors that can affect whether or not you actually see the solid form. So even though the solubility rules say, hey, if you put these two things together, you should get a solid, there's a lot of situations or factors that could actually play a role in you maybe not seeing the solid form. The second thing that sometimes people misunderstand about insoluble things or insoluble salts is the idea that they think it is 100% a solid. And the actual thing is, even things that are insoluble have a small degree of solubility. So something like silver chloride, as you remember, hopefully from your solubility rules, chlorides, bromides, iodines are soluble in everything except for three things: silver, lead 2, and mercury 1. They are the exceptions. So when you take silver and chloride and you put them together, you do get a solid based on solubility rules. But even though you do get this solid, when it's in solution, it will actually still break apart a little bit into its ions. So you get a little bit of the ions still floating around in the solution freely. So it is able to actually set up this equilibrium. And we have our silver chloride that will break apart into its ions, the silver ion and the chloride ion. And because it's able to set up this equilibrium, like anything else, we could write an equilibrium constant for it, which is always our products over our reactants. And that would give us the concentration of silver times the concentration of chloride. And this is what is known as the KSP. And SP stands for solubility product, is what the SP stands for, solubility product. Again, it is basically the equilibrium constant for things that are insoluble. And what we do see here is what I wrote, that pretty much you will only have in your KSP expression the products, because when you write the equilibrium sort of reaction for these type of reactions, it is always solid on the left hand side of the arrow, the reactant side, and they go to aqueous ions on the product side. So that is always how these sort of equations are written, and that means we don't include solid in our equilibrium expression, so you pretty much will only have your products. Now you do it just like any other equilibrium. So if you have some coefficients where things do break apart into more than one ion, you do have to take those coefficients into account. So obviously here we get 2 fluorides. So just like a normal equilibrium constant, you got to take the coefficient into account. We get 2 silvers. We get 3 and 2 of these guys. So again, it works the same way, except really the main difference here is you pretty much will never have a denominator. You'll just have, obviously, the numerator there, and just the products are included. The other thing that's helpful, if you're not familiar with your solubility rules, is you could kind of McFake it. So if you see a KSP value, you could probably assume it's going to be a solid, yeah, and you could treat it like that, and that's how you could write your equation and stuff like that. You find it on a KSP table, again, you could assume it's going to be a solid. Now, with KSP, like I said, there are certain factors that can play a role into whether or not you do see the solid actually form. And one of our good old friends there that help us decide, for example, if we kind of put these two things together, mix these two kind of solutions together, will we get a solid form, is Q. And remember, Q is the reaction quotient. Q is, again, in this case, calculated the same as the KSP. And much like where we can compare Q to the K value and determine, for example, if we're at equilibrium or not, we could compare Q to the KSP value, and that will help us decide whether or not we would expect a solid to form if we mix things together. So if you calculate Q and it's less than the KSP, you will have a unsaturated solution, which means you will not have a precipitate form. If you calculate Q is equal to the KSP, you will have a saturated solution. And a reminder, an unsaturated solution is a solution where you have not hit the maximum amount of solute that will dissolve, right? So you could get everything to dissolve. And you can get this stuff to dissolve all the way up until you hit a saturated solution, which is the solution where you have the maximum amount of solute that you can dissolve at that temperature. Now, if you calculate Q and it's greater than the KSP, you will have a supersaturated solution, which means you would expect a precipitate to form. Now, since all these reactions are written, basically solid goes to aqueous ions, you could go opposite the way this guy is pointing. So if Q is less than the KSP, it will go opposite and you will not get a precipitate. Q is greater than the KSP, go opposite of where that's pointing, you will get a solid. And again, that's a way you can remember it if you want to do that. All right. Here's some KSP values from your table in your book. And again, you may have to reference the table to do some problems. They may not give you the KSP in the actual problem and stuff like that. One of the things that you'll notice from this table is KSP values are super small. These are very small equilibrium values. We got to the minus 39 over there, minus 45, minus 10, 15. So they're very, very small up there. It's like a super small one. I think there we go, minus 32 as well. So KSP values are typically very small values. And because they're still equilibrium constant values, it tells us the same thing, right? So if we have our equation with our giant arrows and I have a small value of K, that means when I reach equilibrium, I mainly have reactants, right? And in these type of reactions, as I just mentioned, on the reactant side, that is where you find your solid. So for the most part, this is why we consider these things to be insoluble and will form a solid, because even though they set up this equilibrium, these are very, very small values of K, and they're basically all hanging out there on the left-hand side in the solid sort of version. And again, that's why when we look at those solubility rules, we consider these things to be insoluble, right? They're pretty much mostly insoluble because of that. Any questions on that there? So let's talk a little bit about some calculations, a very common sort of KSP calculations that we do. And when we're looking at solubility, that's usually the main thing that we're oftentimes after when we're doing these type of problems. And there's two types of solubility that we come across. One is the molar solubility, which basically is the molarity. So if you're asked what is the molar solubility of something, you're basically asking to be found what is the moles per liter. The other type of solubility is maybe a more useful sort of version of solubility. Sometimes you are asked to calculate the solubility in grams per liter, right? How many grams you could kind of dissolve in a liter of solution. Now, as professional chemistry students as you are, if you have moles per liter, which is the molar solubility, and you want to end up with grams per liter, which is the kind of basic solubility, what ties those two things together? How do you go from one to the other? It is the molar mass there on the periodic table, right? So the molar mass is what kind of ties those two sort of values together. So if you have the molar solubility, you can use the molar mass to figure out how many grams per liter that is. And obviously vice versa, if you have the grams per liter, you can use the molar mass to figure out the molar solubility for it. So the molar mass is sort of what ties both of those common units of solubility again together. Now, there are two types of calculations in general that you come across with KSP, and one of them you should do an ice table. One of them you don't have to do an ice table, but I would probably recommend doing an ice table because there's a lot of places in these calculations where people screw up, and it's because, well, in some cases you need to multiply the numbers by 3, for example, and you also have to cube it. And a lot of times when people maybe don't do the ice table, they sometimes go, oh, well, I cubed it, so I don't need to like multiply by 3 anymore, or I multiplied by 3, I don't need to cube it. So a lot of times people kind of miss little things along the way. And sometimes if you kind of just do the ice table, even for both of these calculations, a lot of times you won't miss those kind of little things. So the two types of problems that you are usually given in these sort of KSP problems is you will sometimes just be given the solubility of a compound. So they'll say, hey, the solubility of this compound is 0.2 grams per liter. And what you would want to do with that is if it was something like grams per liter, you would want to convert it to moles per liter. You would then want to find the concentrations of each of the ions. And then you could actually just go into the KSP sort of expression and calculate your KSP. Now, again, technically speaking, on that type of problem, you might not really need an ice table. If you understand molarity, you understand how you get the concentration of ions, you might not need it. The second one is kind of just like a basic equilibrium problem. You're pretty much just said, hey, what is the solubility of silver chloride? And all you're given is the KSP value. So that's the only thing given to you is the KSP value. And if you're just given the KSP value, should definitely be probably a nice stable situation. And you would do an ice table, and there's a couple of different things that happen in this table, not extremely different, that we'll talk about. But that will allow you to get to the solubility of the compound. So let's take a look at one here together, and we'll talk about how we kind of get there. All right, so the solubility of silver phosphate, which I'm not sure why the dramatic pause there between those things is Ag3PO4. At 25 degrees is 1.6 times 10 to the minus 5. What is the KSP of silver phosphate? So the first sort of thing that you want to maybe do here is just think about how that thing's going to break apart. And since we are looking for the KSP, it is a safe assumption that this guy is going to be a solid, right? And again, you can assume it's solid. So when silver phosphate breaks apart, it will break apart into 3 silver ions plus a phosphate ion. And that is, again, how it's going to set up the equilibrium, dissociate there in solution. That will allow us to write our KSP expression for this, which once again is really just going to be our product. So it's going to be the silver concentration, and we do need to cube it because of the coefficient. We're going to times it by the phosphate concentration, and that obviously equals the KSP value, which in this particular case is sort of what we're looking for. Now, in this particular problem, again, you don't necessarily have to do an ice table, but I'm going to do an ice table to show you what it looks like first off, and also, again, probably a better way maybe to do it. So initially here, obviously we're not going to worry on the left-hand side about the solid, right, because it's not going to be involved in anything, so we're not going to put any numbers. We are just going to start with zeros going on over here. Now, our change is like normal. Usually we go minuses and pluses. We do that here. Now, we do use actually in these tables usually a different symbol. So normally for the change we use X, right? That's normally we use for the change. Here in these sort of KSP type tables, people typically will use S. And S stands for the molar solubility. Again, a fancy way of saying the molarity, basically, right? So people use S here to stand for the molar solubility in this table. So when we come to our right-hand side, this is going to be plus 3S. Once again, still need to take into account the coefficient. This is going to be plus S. That means when we reach equilibrium, we will have 3S and S. Any questions all on the table there? Now, like normal, what we do at this point, right, is we stick these guys into our equilibrium expression, and we do the same thing here as well. So going into our KSP expression, we will end up with 3S cubed, and that will be times S is going to equal our KSP value. But in this case, we actually don't know the KSP value since that is what we're looking for. So if we look back into the problem, the other piece of information that was given to us was the solubility of silver phosphate is 1.6 times 10 to the minus 5 moles per liter. Moles per liter is molarity, and that is the molar solubility, RS in this case. Yeah. That means at this point, what we could do is just stick the number back into here. And if we do that, we will end up with 3 times 1.6 times 10 to the minus 5 cubed times 1.6 times 10 to the minus 5. And if I find my calculator, there we go. 3 times 1.6 to the minus 5. Want to cube it and times it by 1.6 to the minus 5. Looking like a 1.8 times 10 to the minus 18, a pretty small value of KSP, which is probably normal in this particular case. First off, any questions on that there? Yeah. No, because it's a K value just like any other K value, so it will not have units. But you will, in these type of problems, have to solve for things like molar solubility or solubility in grams per liter. So when you're asked to solve for something like that, you do want to make sure you include the units for those things. Other questions? Now, again, like I said before, you don't necessarily have to do an ice table, but it's a really good idea because, again, like I said, very common with these type of problems. People either forget the three here or they forget to cube it. So just kind of seeing it in front of you with that is sometimes helpful. The reason you don't necessarily have to do it is, again, if you understand molarity and how it works, and this is really just doing the ice table basically without doing the ice table. But because it's a 1 to 3 relationship, the concentration of silver would be 1 3 times that value. And because it's a 1 to 1 relationship, it'd be 1 times that value. And at that point, you could go basically in. But that's basically what you did down here through the ice table. And again, if you understand molarity, you could kind of just get the concentrations, go right into the KSP value. But again, it's a little bit more organized kind of doing it this way. And you probably won't miss some of those threes and extra things that you have to do along the way. Any questions on that? All right, let's try another one here. What is the solubility in grams per liter of silver chloride? The KSP is silver chloride, 1.6 times. Okay, let's take a look. So again, in this situation, this should definitely be a nice table situation whenever you're given just the KSP. So again, silver chloride, if again you don't know your solubility rules, if you see the KSP, you should assume it's probably going to be solid. So we're going to set up our equilibrium here. Again, always solid on the reactant side, breaking apart into its aqueous ions on the product side. That's going to give us our KSP expression of basically silver times chloride here. Silver times our chloride. In this case, we do have the KSP 1 times 6, 1.6 times 10 to the minus 10. So we will start our ice table like normal, zeroing out everybody initially. Our change again using sort of our S for molar solubility. It's going to give us a plus S and a plus S. Again, here each coefficient is 1. That means at equilibrium here, we're going to end up with an S and an S. Any questions on the table here? Just like normal here, we're going to pop it into our expression. That's going to basically give a S times S is equal to 1.6 times 10 to the minus 10. That's basically S squared, right? So a little square root of both sides there, going to get me an S value here of thing. Will give me an S value of 1.26 times 10 to the minus 5. Remember that when we solve for this S, that is the molar solubility. And that basically means that is molarity, right? And that would be the molar solubility of the solid as well, the whole thing. And you may say we didn't do anything over here, but if you do sort of the stoichiometry relationship backwards, that obviously is this value. It's a 1 to 1 relationship backwards, so that will also be the concentration or the molar solubility of the whole thing. So typically when you do these ice tables, you solve for S, even though you're kind of solving it for like the ions on the other side, that is usually the molar solubility of the whole thing. It may not be the molar solubility of the actual ions. So in this case, it is because it's a 1 to 1 relationship. But again, if the ions broke apart into like a 2 to 1 relationship, you would have to multiply really the answer by 2 if you wanted the concentration of that particular ion. So because of that, that is the molar solubility of silver chloride, which obviously here we can then convert into grams per liter. Again, using the molar mass here. So we'll basically just add these guys together. We'll go 107.9 plus 3545. That's or calculator. You could do it. No, no error. Try that again. 143, it looks like. We're going to multiply by it. 143.35 grams per mole. Moles are going to cancel, and we will end up with basically 0.0018 grams per liter is the solubility of silver chloride basically in water. Is that a lot of solubility? That is not. That basically means if you look at that number, you could dissolve freely in that solution 0.002 grams in 1,000 milliliters of water. That's a very, very small amount with a lot of water, right? So in 1,000 milliliters of water, you get 0.002 grams of silver chloride to dissolve. And that basically is why we consider silver chloride to be insoluble, right? So you can pretty much get not a lot of it to dissolve under normal conditions. Any questions on that there? All right, let's try another one here. Calculate the concentration again. Dramatic pause there of aluminum 3. In an aqueous solution of aluminum hydroxide. A lot of fun spacing on these questions. There we go. Just kind of fix it up there. All right, KSP there, 2 times 10 to minus 32. So see what you come up with on this one here. Okay, let's take a look again here. We're pretty much just given the KSP, so that is just roll into the ice table. So we're going to do aluminum hydroxide. We're going to go solid on that because I do see a KSP value. This is going to break apart into aluminum with a +3 and a few hydroxides there coming off. It's going to give us a KSP expression of aluminum concentration times our hydroxide concentration, which we do again need a cube because of the coefficient. And again, that's going to equal 2 times 10 to the minus 32. So starting our ice table here, we're going to go 0 and 0. Change going to be plus s as the coefficient is 1, plus 3s as again the coefficient here is 3. And that's going to get us here an S and a 3S. Any questions on that there? All right, so popping it back into our equilibrium expression gives us an S times a 3S. Once again, don't forget, you got to also cube it as well. And that is going to equal 2 times 10 to the minus 32. At this point, we could kind of clean up the left-hand side there. By the way, it is 27s to the fourth. I say that because people never do the number. They only do the letter and end up with 3s to the fourth. Yes, so don't forget to cube both things inside there, not just, the letter. And that's going to equal 2 times 10 to the minus 32. And again, that would be 3 times 3 times 3 to do that. We're going to divide by 27, and then we're going to take the fourth root of it there. And if we do that, we're going to go 2 to the minus 32 divided by 27. Going to do a little fourth root action. And I'll go scientific notation here. That's going to get you an S value. We'll call it 5.2 times 10 to the minus 9. Although if you're not in scientific notation, you probably got a bunch of zeros with a 5 at the end of your calculator. And that's just ran out of room there along the way. Same answer. You're good. Any questions on that? By the way, to do the fourth root there, if you have a button on your calculator that looks like that, you could use that. If you don't have a button that has like an X over a square root type thing, looks like that on a lot of calculators. If you don't, you could caret it, the number, take it to a caret, open a parentheses, do 1 divided by 4. Yeah, that will do it for you. 1 divided by 2, take the square root. 1 divided by 3, we'll do the cubed root. In case you can't find that button or not sure how to use it, that will also do it for you as well. So in terms of the question here, we're looking for the concentration of aluminum here at equilibrium. Aluminum ions at equilibrium does equal S, which means it would be 5.2 times 10 to the minus 9 molar. It wasn't asked, but we could also get hydroxides at equilibrium. As I was mentioning a second ago, it is not equal to S, right? At equilibrium is equal to 3S, right? So the concentration of hydroxide would be 3 times S, which if you did that would be that times 3, like a 1 point, we'll call it 6 times 10 to the minus 8 molar, which, by the way, can also be very helpful in some things that we've talked about previously. This would then be the hydroxide concentration, which would allow you perhaps to figure out the pOH if you wanted to. And you could also figure out the pH of this solution by doing so, since we do have the hydroxide given to us. So if you have an insoluble salt like this with the KSP and you're able to figure out the hydroxide concentration like we were here, you could actually figure out the baseline pH of this solution. Or if you had something like H plus or H3O plus on the other side, you could also figure out the pH from that as well. Any questions on that there? Yeah. It's from the formula here, right? That's what the 3 means, right? So the 3 on the bottom means basically you got 3 of those guys inside, and that's basically hydroxide. So that's basically what that 3 on the bottom means, that you get 3 of those. And the reason we have 3 of those is back to really just the basic ionic compound, right? When you have an ionic compound, which is pretty much what all these are, the overall charging is equal to 0, right? And since the aluminum is group 3, it has a plus 3 charge. That's why we need, in this particular case, 3 of those hydroxides to get to it. Yeah. Other questions? All right. We'll skip that. So let's talk a little bit about using KSP values to help us decide a little bit about solubility. And if you had different sort of salts or compounds here, ionic compounds that you wanted to kind of put in order in terms of solubility, you can use the KSP values directly to compare solubilities in certain situations. So, for example, if I look at silver iodide like it shows there, when that breaks apart, I get a silver ion and an iodide ion. If I look at copper 1 iodide, I get a copper 1 ion and an iodide. If I look at our friend calcium sulfate, when that breaks apart, I get a calcium ion and a sulfate ion. Now, what all 3 of these sort of compounds have in common is the number of ions they form. This guy forms 2 ions, this guy forms 2 ions, and this guy forms a grand total of 2 ions when it breaks apart in solution. Because these all form 2 ions, you can directly use the KSP values to make an opinion about which one should be more soluble, which one should be less soluble. The reason that is if you mathematically solve for the molar solubility of each of these guys, because they all break apart into the same number of ions, you basically be doing the same math. So you can directly kind of compare the numbers at the end, and the KSP values can be compared at the end as well. So what does KSP mean in this situation? Well, KSP, if it's large, means we have more products, and products in these reactions are aqueous ions, and they should be more soluble. So in this case, if you looked up the KSP value, you would see that the calcium sulfate has the largest KSP value. The silver iodide has the smallest. So if you had, for example, the copper 1 iodide here and the silver iodide are really just these copper and the silver floating around in a solution. If you add iodide to it, you would expect the silver to come out of solution first because it's least soluble. So if you added something into that solution to precipitate it out, you would expect the silver basically to come out of solution first, followed by the copper, and then lastly, if you actually had the sulfate in there, or the calcium in there, it would be the last one that would come out. So you can look at the KSP directly, and the one with the higher KSP value should be more soluble. If you are comparing 2 things, 3 things, however many things, and they all break apart into the same number of ions. Now, if they do not break apart into the same number of ions, you cannot use the KSP values directly to compare solubility. So if you were taking something like this, where you had copper 2 sulfide, that'll give you a copper 2 and a sulfide. That is 2 ions. If you looked at silver sulfide, you'll get a couple of silvers and a sulfide. That is 3 ions. And if you look at this guy, I won't draw it out, but you'll get like 5 ions in this case. So in this particular case, we have things that are basically breaking apart into different numbers of ions. And because of that, that does affect really the calculation and the solubility because you have different amounts of ions floating around in that solution. Now, if you looked up the KSP values for each of these things, you would see that copper 2 sulfate is times 10 to the minus 45, silver sulfide is to the minus 49, and bismuth 3 sulfide is to the minus 73. So, based on the KSP, if you went in that order, you would say that is the largest KSP, and this guy should be the most soluble. And this guy should be the least soluble based on KSP. But if you actually did the calculations, like the problems we just did a second ago, you would see that the molar solubility of copper 2 sulfide is to the minus 23, and the molar solubility of the bismuth 3 sulfide is to the minus 15. This is actually a bigger molar solubility, right? Bigger, smaller negative exponent, larger number. This is smaller. It's actually the opposite order. This is actually the most soluble. This is actually the least soluble. So in this situation, you cannot use the KSP value to directly compare because they do not break apart into the same number of ions. So what you just want to remember is you want to compare, like the old saying, apples to apples, right? So you can only compare in this situation KSP values if they break apart into the same number of ions. If they don't, you actually have to go physically do the calculation and then compare what you get as a result of that. Any questions on that? All right, so earlier I mentioned that there are definitely several factors that affect solubility, and we're going to talk about some of these factors right now. The first factor that affects solubility, for example, is the common ion effect. And we saw the common ion effect obviously in the last chapter when we talked about buffers. And the presence of a common ion effect, like we see with acids and bases, is it will actually decrease the solubility of a salt. Why does it decrease the solubility of a salt? If you think about the KSP sort of reaction, as I mentioned, you have solid on the left-hand side of the arrow, and you have aqueous ions on the right-hand side of the arrow, which means in this situation, the only place you could have a common ion would be on which side of the arrow? You could only have a common ion on this side of the arrow because that's where you find the ions, right? And if we have a common ion on this side of the arrow, our good friend Le Chatelier's principle will say it will shift which way? It will shift away from it, right? And it's going to decrease the solubility. It's going to force that thing to stay together as a solid. So one thing that can affect the solubility of something is the presence of that common ion. Very similar to what we see in, again, acids and bases, is it will actually shift it and kind of keep it together. So for example, we take a look here at the molar solubility of silver bromide in water versus it in a sodium bromide solution. Let's take a look at it in water first. So in water, once again, it's just going to break apart into its ions. And if we write our KSP, it is going to be silver times bromide, and that's going to equal 7.7 times 10 to the minus 13. So we'll do our ice table here. We're going to go 0 and 0. We're going to do our change, a little plus S and plus S action. And we're going to get S and S. Again, putting this into our expression, that basically is going to give us S squared is equal to 7.7 times 10 to the minus 13. And that S there is then going to equal, after we take the square root, square root, there it is, 7.7 to the minus 13. We're going to look at about an 8.8 times 10 to the minus 7 molar solubility, moles per liter. By the way, if we multiply that by the molar mass of silver bromide, which is 107.9 plus 7990, which will give us a molar mass there of about 187.8 moles per grams per mole. I'll get that right, grams per mole for the periodic table. We will end up with a solubility of this guy of 0.123165 grams per liter, right? So that is our molar solubility, and that is our grams per liter. By the way, also not super soluble either under normal conditions. You could basically, again, get 0.0002 grams of it in 1,000 milliliters of water. Now, what happens if we have this in a solution that also contains sodium bromide? Well, the silver bromide will still set up its equilibrium here in B. And the difference, though, is we now have some sodium bromide there, and sodium bromide is a strong electrolyte, which means it is going to break apart into a sodium ion and a bromide ion. And it is the bromide ion that is the common ion here, right, between those two things. And that means what this affects is initially we have none of the silver, but we do have some bromide being supplied by the sodium bromide, and that's going to be 0.001 here. So we do have an initial concentration. Very similar to when we did kind of like a buffer thing, right? You need somebody on the right-hand side there. That common ion there is the same idea. Change is going to be plus S and plus S. This means at equilibrium, we're going to have S and 0.001 plus S. Just like we did on the other side, we're going to go into our expression. That's going to be S, and 0.001 plus S will equal our KSP of 7.7 times 10 to the minus 13. Definitely KSPs are small values of K, which when we do small values of K, we like to do an assumption, right? And here we could actually do the same thing. We could assume that S is equal to 0 in this case. Just like we did before, it will just be the S's you're adding or subtracting, right, from a number. And that would then get us 0.001 times S equals 7.7 times 10 to the minus 13. Obviously, dividing to the other side. Gonna get us here 7.7 to the minus 13 divided by 0.001. Gonna get us a 7.7 times 10 to the minus 10. And that would be our molar solubility here in the common ion. If we multiply that by our 187.8, which is our molar mass, I'll even write the right units this time. There we go. We're going to end up with a solubility in terms of grams per mole, grams per liter of 1.4 times 10 to the minus 7 grams per liter in this particular case. So in this particular case, we can see that it is more soluble in which one? It is definitely more soluble in water in this case, right? And again, the solubility gets even worse. Instead of like 3 zeros, you got like 6 zeros in front of that guy before you get to it. And the reason for that, again, is those common ions going to push the equilibrium back to the left and decrease the solubility in this particular case. Question on that? Yeah. Yeah, you could check it. I didn't here. You probably should, but I'll be honest with you, because they're so small, you're usually gonna be okay. But if we check it, we would check it the same way. So in this case, we would take our 7.7 to the minus 10 and divide it by 0.001, and you're like nowhere even near like 1%. So You should technically check it. It usually will be pretty okay in these situations, but you would check it the same way we do X as well. Yeah. Other questions? All right, so let's take a look at one here. Yeah, this one. Yeah. Let's see here. The KSP of silver chromate is 9 times 10 to the minus 12. What would be the solubility of this compound in a solution that has 0.1 molar potassium chromate? We'll go with the sol. All right, let's take a look. So again here, we got the KSP of silver chromate. We're in a solution that also has potassium chromate, so probably just by the name there, chromate here is going to be our common ion. So we could set up the equilibrium, which is going to be what the KSP guy will do, right? And that's going to be a solid. That's going to break apart. We are going to get a couple of silver ions in this case, as that 2 goes to the front. And that's going to give us chromate, which is a 2 minus in that case. That will give us a KSP of silver. That does need to be squared because of the coefficient times the chromate here. And that's going to equal 9 times 10 to the minus 12. Obviously, in this case, we do have it in a solution of potassium chromate, which is K2CrO4. That is a strong electrolyte. We'll break apart into 2 potassiums and a chromate. And again, the concentration of this whole thing is 0.1 molar. It is a 1-to-1 relationship between the whole thing and the chromate, which means the concentration of the chromate ion is 1 times 0.1 molar, or still 0.1 molar, right? So again, remember that you can rate the concentration of the whole thing to its ions by how many it breaks apart into. If it breaks apart into 2 and you need that guy, you multiply the concentration by 2. Where that affects, again, our ice table here is right here. Again, we do need a number there, otherwise it is not a common ion here. And that is going to be the 0.1 molar. That once again is going to be supplied by the potassium chromate in this case. Here we'll go with plus 2s. Once again, don't forget the coefficient there. Plus an s. That's going to get us 2s and 0.1 plus s. Any questions on the table or anything like that? All right, so normal procedure here. Going to roll into our KSP up there, but I'll put it down here. So we can go 2s squared. That's going to get us a 0.1 plus s equals 9 times 10 to the minus 12. Once again, you could definitely make an assumption here, so you don't have to do any sort of quadratic type stuff. We're going to get rid of that guy. And that's going to then get us here, let's see, that's going to get us a 4s squared times 0.1 is equal to 9 times 10 to the minus 12, kind of cleaning that up there. That's basically 4 times 0.1. That's going to get us a 0.4 s squared. So at this point, we're going to divide and then square root afterwards. Yeah, so divide and then square root. And if we do that, 9 to the minus 12 divided by 0.4 and square rooting it. Maybe. We can find the right button, square rooting that there. There we go. And that's going to get us here again a molar solubility. Looks like call it 4.7 times 10 to the minus 6. Again, that is going to be our molar solubility. Once again, of really this whole thing. Yeah. Any questions on that there? Okay, so we're going to continue on. Any questions so far? All right. So we just talked about obviously common ion, which, as I mentioned, is one of the things that can affect solubility. There are a couple other things here we're going to talk about that will, again, also have the ability to affect solubility. One big thing that can affect solubility is pH, and pH can play a really big role in terms of solubility. Although we don't do these experiments here anymore, this class used to have a bunch of experiments that were all about selectively precipitating out ions from solution. They're known as qualitative analysis experiments. And if you ever read the instructions on those experiments, they're kind of weird instructions sometimes. And they tell you, in the first part of the sentence, make your solution acidic. And then literally the next sentence is make it basic and then make it acidic again. And there's a lot of these weird sort of instructions. And really, the reason for that is what we're going to talk about here. pH plays a really big role in terms of, in certain situations, as to whether or not, for example, if you wanted to precipitate something out, if you don't have sort of the right pH environment, it will not precipitate out as a solid. It'll just stay there floating around. And it's a really big role, especially when we're dealing with things, insoluble acids or insoluble bases. pH plays a really, really big role in it. So the presence of a common ion, as we just saw there, does decrease the solubility. When we have an insoluble base, they typically will be soluble in acids, and vice versa. If you have an insoluble acid, they typically will be soluble in bases. So let's take a look at magnesium hydroxide here. And magnesium hydroxide is obviously more of a basic type solution since we have hydroxide present. And it will break apart into magnesium ion and a couple of hydroxides. And the KSP for magnesium hydroxide is 1.2 times 10 to the minus 11. So if we ran through sort of a calculation like we did previously, where we'll do our, actually, I'll just kind of put this number up here, 1.2 times 10 to the minus 11. That way I could just steal this here. So if we ran through a nice table and we did our 0 and our 0, we did our plus s and our plus 2s once again for the coefficients. We will end up with s and 2s. And obviously here, as we saw there, we would go into our KSP expression, which once again is our magnesium and our hydroxide squared. Putting that in there will give us s times 2s squared is equal to the KSP value of 1.2 times 10 to the minus 11. That again is going to give us a 4s cubed. Remember, don't forget to square the 2 as well. Going to get us 1.2 times 10 to the minus 11. So we're going to divide by 4 there. And then we're going to take the cube root there of it. So we'll go 1.2 to the minus 11 divided by 4, and then a little cube root action, maybe. I'll try that. And that's going to give us a molar solubility here of 1.4 times 10 to the minus 4 molar. That obviously would be the molar solubility of our magnesium hydroxide in solution. That would also be the concentration of the magnesium ions that would be floating around the solution. But as I mentioned a little earlier ago, we do have hydroxide here, which means if I want the concentration of hydroxide at this point, it would equal 2 times S. So taking my 2 times my 1.4 times 10 to the minus 4, that will give me my concentration of hydroxide. And here I'm just going to use the non-rounded number on my calculator, and I'll get something like 2.9 times 10 to the minus 4 molar. What that's going to allow me to do, obviously, here is calculate the pH of this particular solution. So since that is the hydroxide concentration, I could get the pOH here by taking minus the log of 2.9 times 10 to the minus 4. And that's going to get me there. About a 3.54. And if I subtract 14, I will have my pH of this solution. And that's about a 10.46. So first off, any question on that part of the calculation? So you can see as well, You can use sort of KSP in certain situations to figure out the pH of this solution. So what does that mean? That means basically if you have that beaker sitting there, or flask sitting there of this solution, it's basically should have like a pH around 10.46 in this case. So now we're going to talk about what will happen in this situation if we kind of play with the pH. So let's say that we decided to lower the pH less than 10.46. Now, if I wanted to lower a pH of a solution, I most likely would add what to it? An acid or a base? I would add an acid. That seems like a good answer. And when I add an acid, that's essentially adding H plus, right? And when I add this acid to the solution of magnesium hydroxide, what's going to happen in this situation? What's going to happen with, say, the H plus? Will it do anything? When we look at the equilibrium, is there H plus in the equilibrium? There's not. Is there anything H plus likes in the equilibrium? I'm going to say it likes hydroxide, right? Because when you have H plus and you have OH minus, you make our friend water, yeah? So when you add the acid to this solution, the H plus is going to react with the hydroxide here and form water. That is essentially going to do what in terms of the hydroxide concentration? Increase it or decrease it? Decrease it. And Le Chatelier's principle will say it then should shift which way? It should shift to the right, right? Because you just created a hole over there. And what that's going to do is increase the solubility of this, right? So if we get this equilibrium to shift to the right, it's all ions on that side, all aqueous on that side. That's going to increase the solubility of this. So if I had this solution and I wanted to get some of my magnesium hydroxide to start to dissolve, I need to dump a little acid in there and it's going to actually get it to dissolve, right? By the way, do I need to make this completely acidic to see that happen? I don't. I just need to get it less than 10.46. I could drop it down to 9 and I probably get a lot of it to dissolve, a lot more than I would at 10.46. So you don't have to get it all the way down to an acidic pH to get that effect to occur. You just need to get it below its baseline pH of 10.46 and you will start to see that occur. So we would start to lower it less than 10.46 and then that should increase the solubility of this by just playing obviously with the pH. Any questions on that there? Now the opposite is sort of true here. If I decide to take the pH higher than 10.46, I most likely would be adding a base in this case. And when you add a base, you typically have hydroxide in that situation. Now what happens in this equilibrium is I am actually adding more hydroxide, right, to this equilibrium. So I am now building up myself a lot more hydroxide in this situation. And once again, Le Chatelier's principle is going to tell us that if I build up a bunch of hydroxide on the right-hand side, it's going to shift away from it, right? And it's now going to move to the left-hand side in this case. And what does that mean about solubility? Is it going to increase or decrease? Going to decrease, right? Because we're shifting it to the solid side. So the solubility here will start to decrease in this case. And again, that's because of the buildup of hydroxide. So you can see in a solution that is an insoluble base or an acid, you could actually calculate kind of your baseline pH for that solution. And you can make minor adjustments even in the pH up or down. And that could have a pretty big effect on the solubility. So in this case, if I wanted more solid, all I have to do is just kick the pH above 10.46 and I'll start to see more solid form. And again, if I wanted to, I could play with it and just add some acid and it'll go back the other way, and we'll start to see a lot of the solid decrease. Any questions on the effect of pH here? So again, this is what it means above where we say if you have an insoluble base like what we have here, it is soluble in acidic solutions. If you add an acid, it will cause the equilibrium to shift towards the ions and vice versa, obviously, in this case. Now, the third sort of effect on solubility, so far we talked about common ion, we talked about pH. The third effect on solubility is actually concentration. Now, you could have solubility rules that say if you put these two things together, you should get a solid that forms. But if you do not have the right concentration of those ions in solution, you may not see the solid actually form. And that type of experiments I was talking about earlier, those qualitative analysis experiments, that's a very common problem that sometimes occurs because even not in those type of experiments, every time we add solution to another solution, to some more reagents, or we go to the bottles and we drop some in, we add maybe a little more than we should, right? And all that good stuff. What we're essentially doing every time we add a reagent to your test tube, to your beaker, to all that, we're essentially doing dilution, right? We're diluting it down, which means in this type of situation, if you're looking to, for example, precipitate out ions that are floating around, if you add too much reagents, you're just going to drop your concentration maybe too low to actually see the precipitate form, even though it should form. So it is possible that concentration plays a really big role as to whether or not, again, that you'll kind of see the precipitate happen or not. And that's really where we talked about a little bit earlier. Q comes in. Again, as we talked about at the beginning there, Q is calculated the same as the KSP. And we can compare the Q to the KSP to determine whether or not a precipitate will form. And if our Q is greater than the KSP, we would expect the solid to form. But if our Q is less, we would not expect it to form. So let's take a look at this problem here and see what we're talking about in terms of whether or not we expect the precipitate to form. Now, if we were to take 2 milliliters of a 0.2 molar sodium hydroxide solution and we mixed it with 1 liter of a 0.1 molar calcium chloride solution, what we want to know is, will we get a precipitate form? So one of the first things you want to kind of think about is there any combination here based on solubility rules that would perhaps form a precipitate? So hopefully you know that sodium hydroxide is basically a source of sodium ions and hydroxide ions, and calcium chloride is a source of calcium ions and chloride ions. So the option here is to switch partners, right? So if you know your solubility rules and you got something like sodium chloride, you know that is probably not going to make a solid, right? Because sodium is pretty much soluble in everything. So that leaves you your calcium and hydroxide coming together. And in terms of solubility, that actually is a possible solid that would form, as hydroxide is typically insoluble except for things like in group 1 or ammonium. And that's your possible thing. So looking at our options and putting them together, this is our one sort of option of what could happen and could form a solid. We could also obviously look up the KSP value for that in a table. And if we looked up the KSP value for that in a table, that's going to give us a KSP for calcium hydroxide of 8 times 10 to the minus 6. So in this situation, to compare whether or not we will sort of get the solid to form, we do want to calculate Q. And once again, Q is calculated the exact same way as our calcium, as our KSP. And our calcium hydroxide would break apart, obviously, into a calcium ion and 2 hydroxide ions here. And that will essentially give us a Q and a KSP expression of calcium times hydroxide squared. Now, what we need in this case is the concentration or molarity of the calcium ions and the hydroxide ions in solution. So we are essentially taking 2 milliliters of 0.2 molar sodium hydroxide, and we're going to mix it with 1 liter. I'm going to actually convert it into milliliters so everybody's in the same sort of units. So 1,000 milliliters is 1 liter of 0.1 molar calcium chloride. So the first thing we want to figure out here is the calcium concentration. So obviously the only source of calcium is going to come from our calcium chloride. So that's going to be our source of calcium ions in the solution when we basically throw it together up here and they all go for a swim. This again is, as I just mentioned, a dilution like we've done many times throughout the semester here, right? So we have to use something like M1V1 equals M2V2 to get the concentration of calcium in the mixture. So a little M1V1 equals M2V2 action there. So we'll go with our 0.1 molar, which is the concentration of our calcium, and our 1,000 milliliters. By the way, in this case, when we look at calcium chloride, it breaks apart into a calcium and two chlorides. And if the concentration of the whole thing is zero point 0.1 molar, it is a 1-to-1 relationship between that and the calcium, which means the calcium's concentration would also be zero point 0.1 molar. By the way, we don't need it in this problem, but what would the chloride's concentration be? We need to do what with it? We need to multiply it by 2, yeah? So the chloride's concentration here would actually be 0.2 molar, but again, we don't need it in this problem. So because it's a 1-to-1 relationship between the calcium chloride and the calcium ions, we know the concentration of calcium ions is 0.1. Here, we're going to do M2, which would give us our calcium concentration. And our V2 is our total volume. So again, this is why I kind of converted it into the same units. That's a 1,002 milliliters total volume by adding these two guys together, right? So if I do that, we're going to go 0.1 times 1,000 divided by 1,002. There we go. And that's going to give me a calcium concentration of 0.0998. I'm going to do a similar calculation for my source of hydroxide. And obviously, in this case, my source of hydroxide is the sodium hydroxide. It also is a 1-to-1 relationship between sodium hydroxide and hydroxide. So again, same idea. Sodium hydroxide will break apart into a sodium and one hydroxide. So if the concentration of this guy is 0.2, this guy will also be 0.2, as it's a 1-to-1 relationship between it. So putting the numbers in here, we have 0.2 molar for our hydroxide. And we're using 2 milliliters of it. Once again, our total volume when we mix it all together is 1,002 milliliters at this point. So we will end up with 0.2 times 2 divided by 1,002. And that's going to get us here a concentration of hydroxide, we'll call it 3.99 times 10 to the minus 4 molar. Any questions on that there? All right, now that we have the concentrations of the calcium in the solution and the hydroxide in the solution, we could put it into our Q value there, and we'll do that. So our calcium was 0.0998, looks like. And our hydroxide was 3.99 times 10 to the minus 4 squared. Don't forget, again, you still need to square it. And we're going to do a little squaring of that, and then times that by 0.0998. That's going to get us a Q value of 1.6 times 10 to the minus 8. Any questions on the Q calculation here? All right, now that we have our Q, we can compare it to our KSP. And in this particular case, our KSP was somewhere. Where did it go? Did I lose it? I did lose it. There it is. I wrote over it. 1 point, what was that? To the minus 6, I think. Let me erase some of that there. There we go. There it is. So it is 8 to the minus 6, looks like, as I uncover it there. So in this particular case, which one is bigger, the KSP or the Q? KSP is bigger. That means, would I expect to precipitate in this case? I would not. Again, it should head the opposite way that's pointing, and that's to the product side where we have aqueous ions. So in this case, we should expect no precipitate. And again, this is an illustration that even though solubility rules tells us if we put those two things together, we should actually see a solid. In this particular case, we will not see a solid because of the concentrations of the ions in the solutions are not proper enough for us to actually see the solid form. Any questions on that? So those are three really big factors that affect solubility: pH, common ion, and the actual concentration of the ions that are floating around in the solutions. If any of those are sort of out of whack for what you want to kind of precipitate out or see a solid form, you may actually not see the solid form when the solubility rules tell you it does. So it's a good reminder that, solubility rules aren't like 100% always happening in those situations. There's a lot of outside factors that play a really big effect on solubility, and you got to take all those into sort of consideration when you're doing it. Any questions on that there? So the next thing we're going to talk about is sort of related to everything that we kind of been talking about, and it really is more specifically related to those type of experiments that we don't do anymore around here. And this is what is sometimes referred to as selective precipitation. And the idea is, especially like I said, when you would do these type of experiments that were very common in this type of class many years ago, um, you would have basically a beaker or a test tube that has a bunch of ions floating around. And the idea is you want to precipitate out just certain ones that are floating around and leave the other ones perfectly fine, still floating around. And that's the idea there of selective precipitation. So, for example, in this one, if we had like a beaker there and we had both bromide ions floating around and chloride ions floating around in this beaker, we could definitely precipitate out those ions as solids by adding something like silver nitrate, which is like a source of silver ions. And that is because when I do that based on solubility rules, I should get a silver bromide solid form. And I should also get a silver chloride solid that would form as silver is being used as our precipitating reagent in this case to make those solids. Now, if I was not super careful when I did this, but I was interested in kind of individually precipitating these ions out, and I just grabbed any old bottle off the shelf of silver nitrate and I just dumped it in there, I would definitely see some solid form. The problem is the picture there, one is silver bromide and one is silver chloride. They are essentially both white solids, which means if you're not very careful when you do this, you're going to get a bunch of white solid that comes out, and you got to go, well, I think like this one's like the silver chloride, maybe this one is the silver bromide. I have no idea. You're not going to be able to really individually precipitate those out if you're not really careful. But we can definitely use the KSP to our advantage. And one of the big advantages of KSP is it will allow us to figure out, for example, if we want to precipitate out an ion and keep the other ion in solution, we could actually figure out how much of that precipitating reagent we would need to put in there to actually see a precipitate form. And that's a very helpful thing here. So if we look at our two options here and we look at the KSPs here, we could look up the KSP values for our two options of solid that will form in this example. We could have obviously our silver bromide, which would break apart into silver ions and bromide ions, and a KSP of 7.7 times 10 to the minus 13. And we could also have silver chloride as an option that would obviously break into silver ions and chloride ions with a KSP of 1.6 times 10 to the minus 10. So in this particular problem, we know one thing, which is we know the concentration of these ions that are floating around in this solution has a concentration of 0.02 molar. So our goal in this is to figure out how much silver ion we need to throw in there. And again, this could be something like silver nitrate, which would be a source of silver. We need to figure out how much of that to only precipitate out the bromide. So in this case, what we want to do is get this guy to precipitate out, but leave the chloride ions still really floating around in the solution. So once again, like I said, we could use KSP to help us figure this out. If we were to write our KSP expression here for silver bromide, our KSP again is going to be our silver ion times our bromide ion. and that's going to equal 7.7 times 10 to the minus 13. Now, in this particular case, I'm interested in how much silver I would need to put in there to actually see the silver bromide start to precipitate out. So I could rearrange this KSP expression and solve for silver. And this equals 7.7 times 10 to the minus 13 divided by the bromide concentration. That's okay because I do know the bromide concentration in this solution is 0.02 molar, which means if I put this into here, 7.7 times 10 to the minus 13 divided by the bromide concentration that's floating around in that solution, I will end up with a value of 7.7 to the minus 13 divided by 0.02, a value of about 3.9 times 10 to the minus 11 molar. So what does that number really represent? That number represents the minimum amount of silver in this example needed to see silver bromide precipitate out of solution. So if you want to see silver bromide precipitate out of that solution, you have to come in with at least a concentration of silver of 3.9 times 10 to the minus 11. By the way, if you come in with silver less than that concentration, nothing's going to happen. It's not enough to get it to precipitate out. So you got to have a minimum amount of silver that is at least that amount or more to allow the bromide ions to precipitate out of solution. Any questions on that there? Now, what about silver chloride? What do I need to get silver chloride to precipitate out? I could do a similar calculation for silver chloride. The KSP is going to be our silver times our chloride, and that's going to equal 1.6 times 10 to the minus 10. Once again, here I can rearrange and solve for silver, which will be 1.6 times 10 to the minus 10 divided by our chloride concentration. Once again, our chloride is the same as the bromide. And we go 1.6 times 10 to the minus 10 divided by 0.02. And that's going to get us here 8.0 times 10 to the minus 9 molar. What does that number represent? That number represents the minimum amount of silver you need to start to see chloride come out of solution as a solid. That is the minimum amount of silver to see the silver chloride precipitate out, basically, in this case. Which one's larger? For the silver chloride concentration, right? And that's good because in this case, we want to precipitate out silver bromide first, right? So what that means is if you want to take out of solution just the silver bromide, but leave the chloride ions happily floating around still in the solution, you need to have a silver concentration that is greater than 3.9 times 10 to the minus 11. But I cannot have my silver concentration go over this number, right? Otherwise, now I'm going to get the other guy to come out. I got to keep it less than 8 times 10 to the minus 9 molar in this case. And if you do that, you will actually see and be able to individually precipitate out both of those ions from solution one at a time. So if you were doing this and you had your test tube or you had maybe a test tube of it, both of those ions floating around, you would add some like silver nitrate, get it to a concentration of 3.9 times 10 to the minus 11, and you should start to see some solid coming out. And when you see that solid coming out, you should feel pretty confident that that is the silver bromide because that's not enough silver to get the chloride out of solution. And you could keep adding, you could even increase the silver concentration if you wanted to, and you'll see some more solid come out, more solid come out. At some point, you'll probably stop seeing solid come out, right? And at that point, you can feel pretty confident that you have now removed all the bromide from the solution. Now, if you want to remove the chloride, you then need to increase your silver concentration now up to 8 times 10 to the minus 9. And when you do that, you will once again start to see some white solid come out. And you can feel very confident that that solid that you're seeing is the silver chloride at this point. And now you can precipitate out the silver chloride until you see no more solid. And at that point, you have now selectively precipitated out both ions from solution, right? Again, if I was not super careful and I just dropped in a silver concentration above 8 times 10 to the minus 9, what will happen? If I went way high with my silver concentration, everybody's coming out together, right? So again, you're going to get that problem of everybody's just going to precipitate out together because it's enough for everybody to precipitate at that point. So if I grab like the 1 molar bottle of silver nitrate, everybody's coming out of the pool all together, right? Everybody's coming out as a solid. You'll have no idea as which one's which, obviously, because again, they look very similar to each other when they're in the solution. Any questions on that? Now, to tie this together is something we talked about earlier. Dare I do that? Is both of these guys break apart into how many ions? 2, which means we can directly use the KSP values in this case to figure out which one should be more soluble and which one has the larger KSP value in this case. The silver chloride, which means between silver chloride and silver bromide, the silver chloride should be more soluble, which is why the question is asked the way it is, right? Because the bromide, no matter what you do, is going to come out first because it's less soluble than the chloride. So there would be no way in this case to take the chloride out without taking the bromide with it, right? So if you were doing this, you could use KSP to your advantage to know, oh, in this situation, I got to hit the bromide first and then take the chloride out if I want to separate them out, because you cannot do it the other way around because the KSP tells us that as well. So these are really big things that the KSP can really help you understand. And even in a practical aspect, if you want to do something like selective precipitation, it could tell you how much of a precipitating reagent you need to do that. It could also tell you, in some cases, the order of how it should come out of solution. And again, even if you were comparing two things that didn't have the same KSP, you could technically do the calculation of solubility for both of them and see which one would be more soluble, right, in that situation. And it will also help you figure those things out. Any questions on selective precipitation? No? All right. So as I mentioned before, and we'll just talk a little bit about it. Again, we don't actually do these experiments anymore. A couple colleges still do it. When I first started teaching, this class was all these experiments. You never did anything else but these experiments. So at like all these colleges, which was funny because the whole class was about everything else except this is one little section of one chapter, and that used to be like the entire lab portion of it. But these qualitative analysis experiments are really what I was just talking about. It's really selective precipitation. And the idea is you have different groups of ions that are related to each other. There's group 1, group 2, group 3, group 4, and sometimes 5, and 4 and 5 are sometimes comboed together. But the groups here are not the groups on the periodic table. They are grouped together based on solubility rules. So as we talked about a second ago, things like chloride are soluble in everything except for these 3 members of group 1, silver, lead, and mercury. And each of these groups have a precipitating reagent. So for example, to get rid of group 1, if you had a beaker of all 4 of these group members floating around, all these ions floating around in this solution, you wanted to just precipitate out group 1 to start your experiment and leave everybody else floating around, you would add something like hydrochloric acid to it. And the hydrochloric acid in this case is a source of chloride. And based on solubility rules, that's going to allow all the members of group 1 to basically come out of the pool, and they're going to come down as a solid at this point. And what you would do at this point is pour off the liquid. You would centrifuge it, pour off the liquid, you have the solid. And then from that solid, what you typically do is now separate out all the group 1 members from each other. And you would have specific tests that at the end you could specifically test and go, oh, this was positive for silver being there, this is positive for mercury, this is positive for lead. For example, if you did that and you had this solid of the silver, the lead, and the mercury one in there. What you would actually do in this case, just to show you what happens at that point, these would all be group one members. And you would do different tests to separate out each of those from each other. You would actually take your solid that has all those guys in it, and you would add some hot water to it, hot deionized water to it, and you would actually put it in hot water. And what happens in that case is you now change the temperature and it gets really hot, and that's good for lead because then what happens is when you heat it up, the lead ions go free and they go out into the solution part. Still in the solid part, you will still have your silver and your mercury hanging out in there. You then can pour off the lead ions that are floating around and you hit it with something like dichromate and you make a solid. You precipitate it out. You hit it with a little dichromate and then you get this nice yellow solid. And you go, cool, I had lead in my solution, right? Now you take this solid that still has the silver and the mercury with it, you hit ammonia, you throw a little base in there. And when you do that, what happens is the silver will jump out of solution and it will actually hook up with the ammonia and it will now have in the solution part the silver that makes a complex ion with ammonia and it's floating around. You will still have this solid down here that has the mercury in it. And that when the mercury and the ammonia hit each other, it now becomes like this grayish solid. And you go, cool, I got a gray solid. I had mercury in my solution, right? And now what you have left over is this silver that's tied up with this ammonia and this complex ion. And we talked about solubility, right? In pH. You hit this thing with some 16 molar nitric acid. Carefully, you should do that, by the way, yes. I want to tell you the story that happened last week. All right. So you're going to hit this with some nitric acid. And what that's going to do is change the pH. And that's going to allow this ammonia to now go away because it's no longer going to be basic. It's going to be really acidic. And it's going to now be NH4 plus. And there's still chloride ions floating around. And these guys will come back together. And you'll see that white solid form. And you go, cool, that's silver chloride that came back. And now you have identified each member of, say, group one by specific tests. And that's the idea of qualitative analysis. It's really just selective precipitation. You precipitate stuff out, you leave stuff float around, you centrifuge, you pour it off, you do these individual tests to each of these. At that point, what you would do, obviously, is go back now and take out group two. And for group two, there's the reagent that group two comes out as. They use hydrogen sulfide gas, which is toxic, smelly, crappy stuff, which is why they don't do these experiments too much anymore. But they use ammonium sulfide sometimes, which is still very smelly as well, just so you know. I was teaching it one time during the summer, and there's a spot where they make the hydrogen sulfide gas actually at that school. They do a reaction that makes the hydrogen sulfide gas. And they do it in fume hoods, so everybody works in a fume hood. And the second everybody in the class hit that step, all the fume hoods shut down. We're like, uh-oh, get that into the waste container quickly, and we're leaving for today. But very, very smelly. But these guys will actually precipitate out using sulfide, hydrogen sulfide. But group three, by the way, will also use sulfide as a precipitating reagent. So you may be saying, how come group two and three maybe doesn't come out of solution at the same time? Again, it's pH that doesn't allow both of them to come out at the same time. When you do group two, you need super acidic, like a pH of 0.5 acidic, super acidic type of solution. And what that does is it creates an environment that's all good for these guys to precipitate out, but that's like way too acidic for those guys to precipitate out. So by controlling that pH, you're able to keep certain guys in solution, precipitate out other guys from solution. And again, that pH, as we talked about, plays a really big role in these things. That's why you get those crazy instructions I mentioned earlier, like make it acidic, nah, make it basic, hey, go back to acidic and stuff like that. And the idea there is to keep the environment correct for what you need to precipitate out and what you need to take out of solution. Then for group 3, you would hit it with the same stuff, but make a very basic solution, and that's going to keep those guys come out. When you get to the end groups, you get things like sodium, potassium, ammonium. And if you think about your solubility rules, those guys are pretty much soluble in everything. So for those guys, especially sodium, potassium, and ammonium, there's really not any type of precipitation test that you could do to identify them. So we come to, for those last group, everybody's favorite thing, which is flame tests. Yeah. So we oftentimes use flame tests to identify things like sodium being present, potassium being present. Ammonium, we actually hit it with some sodium hydroxide, use a little litmus paper, make some ammonium gas, and you could, litmus paper turns blue and goes, cool, that's what's there. There are tests for other things like barium, magnesium. You can make some precipitates. You can also do flame tests for those as well. So when we get to the end, we usually get things that are very soluble in a lot of things. So we have to rely upon certain things like flame tests to sort of do identifications of it. When you're doing any of this type of analysis, you typically do want to do it in order. They're put in order group 1, 2, 3, and 4 based on their solubility sort of rules. So if you had a general unknown where you had a bunch of ions floating around and you wanted to figure out what's in there, you would start with group 1 guys and get them out of the way. And then you know for sure and there's no group 1 left. Then you go to group 2, get them out of the way. And you would do these in a very specific order and basically hopefully get to the end. That's also why maybe they don't do those experiments. Where I used to teach, or I still teach, but they used to do it. They would do nothing but these experiments for cations. There's also anion tests that you would do as well. So there's a bunch of anions that are grouped together. The anion tests are a little bit weirder. There's a lot of smelling in those. So a lot of schools didn't do it. Like, it smells like airplane glue. I'll give it a whiff. That's how you know. So there's like cations and anions. And years ago, what the students would get is they would do all these kind of groups to begin the semester. And at the end, about 2 months left, you would get 2 general unknowns and go after it and try to figure out what's in it. And they would be solid. And people had to figure out how to get them into the solution. That took like a month. And then they had to go through all these tests to try to identify it. It's good times. See how nice and easy it is these days. They don't do these things. All right. Any questions on that there? All right. That's enough of torture part 1. Yes. Torture part 2 will pick up at normal lecture time. And we'll see everybody there.